start our second topic. So week 2. Week 1, as we've been through last week, was just a general introduction. Some basic activities were done over the workshop. And this week, which is week 2, we're going to start talking about important behaviors for that reinforced concrete materials, which going to be the core material used in designing structural systems, including beams, slabs, columns, etc. So just in terms of calculations and how heavy is the topic is, I can still advise that this week is still a bit gentle in terms of the level of calculations that you will be practicing. Creep, shrinkage, durability, and fire resistance. Yes, there are 4 topics, but you're going to see we simply just introducing you to how these terminologies are linked or related to reinforced concrete structures. We all hear in normal life about shrinkage in different materials and different non-structural components, but we're gonna talk about how they are considered in reinforced concrete structures, and more specifically in the design process. Durability and fire resistance, again, they are very important parameters or behaviors need to be determined at the start of the design. In terms of calculations, as I said, not very lengthy calculations you're going to experience, whether today during the worked examples process or session, or also during the workshops tomorrow, because mostly we're just going to be finding some values from tables given in the standards. That's mostly what we're going to be doing, unlike what we're going to do from week 3. Week 3, that will be the start of employing formulas and equations, including some parameters from the standard. So just to get you ready and get you smoothly into the subject. So week 2, and most of the reading materials are actually provided from a LMS, including the standards. So basically the standard will be the key source of most of the tables I was talking about, and they are mostly used to achieve whatever design required. So as I just briefed you before, we will introduce you to creep and shrinkage. We use these 2 names or terminologies in general life, but we're going to see how they are also impacting reinforced concrete structures. After these 2 behaviors, we will talk about durability aspect and also the fire rating aspects for the design. And I can tell you what the designer need to do in terms of satisfying a required durability or fire rating. Basically, he's going to define few parameters on his or her drawings. For example, as we said last week, the cover. You need to clearly define it, make sure it is the cover that was used in your calculations for the strength and serviceability, which we will do next week. So you're going to see next week one of the starting points to do our design. So we will talk to you slowly about a cross section for a reinforced concrete. This is it here, like rectangular cross section, and it's got some few or a number of bars bottom and top. For example, you've got some bars top and bottom. Now the key, the cover here, the cover is the distance between the very top of your beam to the start of your bar. Same thing with the bottoms from here to there. This cover got it's really got strong impact on the strength, capacity, and deflection. So if you did not choose the cover from the start with the careful with the careful considerations for durability and fire resistance, and you've started already the design, the lengthy design, and completed the documentations for the many number of beams and slabs, then you may end up repeating this whole design again to make sure it is correct. So yes, they are very simple steps to go through, but also they have a strong impact on the overall design that you will end up doing. Okay, so 4 things we're going to go through today. They are simple to look after in terms of calculations. The first one we have here, shrinkage, and there's a number of loaded slides, but I will take them. I'll take you through them with some examples. So as I said, if we talk about a sponge, you know, we all have been seeing sponge, and sponge, like when you keep them to dry, what's happening to them? They are reducing in size. They get, you know, they get shortened, and their length's gonna get shortened towards its center of mass. So if you got just a piece of concrete, or let me just check if someone is putting. No, that was not to me. So if you've got a piece of slab or a sponge or any materials that can be affected by shrinkage, then at the start it's wet. Yeah, it's got enough water content, and then with time the water will dry out, and what's going to happen to this rectangular concrete slab? It will shrink to its center of mass. So which in this case, you know, the centroid for this shape, it's just the center, and then shrink. What does it do? It's going to shorten the slab towards its center of mass. So this is practically what shrinkage is about. So it's the process of getting the moisture slowly out of the concrete mix. Now, the shrinkage typically will happen from the liquid state towards the hardened state. So it's only happening during that early stage. That's where cracks can typically happen for poorly constructed concrete sections, or even poorly designed concrete sections if not adequate reinforcement was placed there to cope with that shrinkage. Now, with shrinkage, again, it's not a chemical reaction. There are 2 types, as we're going to summarize later. There is a chemical reaction, depends on what elements are involved inside that mix, and also a drying effect, which is not a chemical reaction. There is 2 things to cause shrinkage, and at the end of our, in 2 slides, we're going to summarize to you somehow that the value of shrinkage, right, is calculated based on 2 components. One of them is the chemical autogeneous shrinkage, which is an experimental value we're simply going to get from the standard. We will plus this or add it to the drying shrinkage, which will happen due to losing the water, or like the water get evaporated from the mix, and that's just naturally happening to any mix, and it's just there. It's just inherently there. This behavior, you just need to deal with it. And this is again one of the differences between steel structures and concrete. Concrete is a complicated chemical related materials that got different processes to go through, and you know, shrinkage was out of the game last year when we showed you how to design steel structures, but it's got an impact for concrete structures. Another thing, if we talk about timber, shrinkage, yes, happens with timber, but it's got simplified formulas to deal with, because timber, yeah, it's a solid material at the start, but still some of the timber types got some sort of moisture, and over time shrinkage can have an impact. However, the standards looked carefully after such issues. So back to concrete, and the second statement here is referring to restraint. What does this mean, or what this statement is talking about? I will just clarify it to you with the sketch I just did. Didn't I just show you from a plan view? This is just a plan view, a rectangular plan view for a slab, right? And the slabs typically sits or supported by walls. I will make it in blue. You've got a wall here, and maybe you've got a wall here, right? Now, statement number 2 is telling you usually when the slab gonna shrink, whether you like it or not. The slab will shrink. What does it mean physically? It means that it will get shortened. Remember here, we're not talking about many millimeters or even a few millimeters. We're talking about 2 or 3 or half of a millimeter, depends on the design. But these millimeters, or these very few micro even millimeters, if you don't deal with them correctly, they're going to end up causing maybe significant cracks or small ugly cracks. Sometimes clients or architects, they like to have a polished finish of concrete, and they intentionally make a request to have polished concrete. Yes, you're always going to say no. Even if you're going to follow the standards from your end as a designer, you're just going to follow the standards, full stop. That's it. And then it's going to be the contractor's role and the supplier's role to supply the correct mix, and the correct products. And they have to also conduct the correct curing process. You remember the watering process and all that. So it's a really complicated process. As a designer, if you are required to have a strong durability or very reduced shrinkage rates in a slab, you just need to follow the standards to achieve it. However, you always need to make the client know that there are other parties involved, and the industry knows this very well. So again, statement 2 here is talking about the problems with shrinkage. Problem with shrinkage is if those slabs, whatever slab we're talking about, they're going to be restrained. We're referring here to restraint. What does restraint means? It will prevent the slab from shrinking. And because we're preventing it from shrinking, cracks will happen. So you're going to have cracks here, cracks there, because we are actually restraining the slab. Why are we restraining it? Because we're supporting it. All right, we're supporting the slab. It has to be physically connected to something. Someone gonna ask me, what about pavement slab, like slab on the ground, sitting on the soil? You got the slab here, right? Say this is one of your, when you walk home, or like the driveway you've got at your home. It's just a concrete slab sitting on soil. Now, my question to you, when they're gonna pour this slab for you, do you think it's gonna cause cracks, or is it restrained? Any thoughts? Slab on the ground. I'm not talking about suspended slabs. Slab on the ground. Do you think this piece of concrete sitting on the soil?
No, it will not make any crack.
Correct. So yeah, thanks for your answer, because the way you looked at it, you consider that it's not restrained. It's just simply gonna slide on the soil, right? And happy days, no problems. However, there is actually friction. There is a friction between the gray concrete and the soil, the dirt. And that friction is causing, as you know from physics, it is causing a force, a resisting force. Now, that resisting force, it can still be considered as a restraining mechanism that will end up causing cracks, because the soil, due to shrinkage, when this slab tries to shrink, it will try to move this way to the center of mass. But Mr. Soil will say no, he will resist that slide, those few millimeters or micromillimeters, whatever. And then the ugly cracks will start happening. So, and if you walk, let me just open another sheet, just open this one. If we open this sheet, sorry, just want to see, do I have a hand? Oops, let me just delete this. Just want to draw another thing for you. So just cleaning this up. Right, so, if we look at a footpath, it's a smaller thickness. So you see mostly in a footpath. This is just a council footpath outside your house, right? They will never pour a slab more than, say, 2 meters without what? They got these kind of lines. They are the sockets, the joints. So sockets basically, if I take a view, if I look at the side of the slab, this is the slab and that's the soil under. Usually they're gonna make a socket here every 2 meters or every 1.5 meters, because if they're gonna keep it too long without a socket, then the whole piece of how many, let's say 10 meters long slab, and usually these are about, say, 1.5 meters wide, depends on the council. So 1.5 meter wide footpath, pouring it as 1 meter length, you're gonna have many cracks in it, right? So what do? They're gonna say every 1 meter or so, we're gonna make a socket, and the socket will be absorbing those cracks. So you see what we have? We're still having shrinkage. We cannot avoid shrinkage, but we're making sockets, so we're gonna absorb the cracks there, and you're gonna have as nice as possible panels without those ugly cracks. Now, just for your information, usually, as you know from physics, and as I just said to you, this is a plan view for a piece of concrete, and it's sitting, whether it's suspended or sitting on the soil. How shrinkage works, the panel will aim to get shortened and shrunk towards its center of mass. So the best shrinking behavior will happen for a simplified shape, and the simplified shape for this is going to be a square. What does this mean to us? It means to us how to determine the sockets. It's best to put the sockets in a way where the shape of the panel going to be as square as possible, right? So someone can ask how frequent we put these sockets. Ideally, you keep them to create a square shape as much as possible. However, you can't, if you've got a long footpath, you don't need to do that, because they're going to still look too much and too ugly, and again, cost time to do so. So usually you can go to the 1:2 ratio. However, someone will tell me, but isn't this going to cause also shrinkage? They can be managed by putting some steel. As we're going to see in the examples for shrinkage, when we put steel can resist those cracks and prevent them. So this is really how it works. I just want you to understand the whole exercise practically. What does the shrinkage? I know we're going to use shrinkage a lot when we do the deflection designs, but and also we're going to do some examples about like it's going to be shortened, whatever. But practically, that's how it works. Yeah, shrinkage is there always, but to prevent it, we can use sockets, or we can put reinforcement. But again, if we only rely on reinforcement, it's going to be too costly. We can't put a lot of reinforcement, so we also employ sockets. I'm talking here about slab on the ground. However, for suspended slabs, yeah, we cannot make sockets. We don't do that. We do movement joints, and this is a different topic which I don't want to get through. So for suspended slab, you're never going to make sockets. You do something different called movement joints. Like, quick example, bridges. You know, when they do the bridge, they don't pour it in one go. They make those movement joints, and they are there to allow for temperature and also shrinkage if it was concrete, as well as right. So that was just giving you an understanding about what we mean with restraining, because all the slabs are restrained, whether sitting on the ground or suspended on walls or columns, and that restraining mechanism will resist the shrinkage, and then it will cause stresses, which when the stresses again goes over what the concrete stresses can take, and last week we talked about the 3 MPa. You remember the 3 or 4 MPa? The 3 and 4 MPa is the maximum tensile stresses. Remember, these stresses under shrinkage, they are tension. And we said concrete is weak in tension. and the best, and like it can take up to 3 for a 25 MPa concrete. So when we reach that 3 MPa, it's gonna crack. To reduce those stresses, we can use saw cuts if it's on the ground, or we can put more steel to help us resist those stresses. So as I said to you before, shrinkage, yeah, that mechanism of shortening will eventually cause increased deflections, and yeah, we're gonna talk about the other effects. So mostly deflections. Yeah, shrinkage is gonna cause deflections. So if it was not correctly calculated, this will add maybe another 15 millimeters into your calculations, which is going to be a problem. And you're going to see when we get to the deflection design in about week 6 or 7, we will show you how these parameters we will introduce to you now are involved inside those many deflection equations we have. Right. For today, we're only introducing simplified parameters. Like I think we're going to use them in the example. Like these two guys, we're just talking here about the design shrinkage is this eta CS. At this stage, we're just telling you it comes from calculating 2 parameters. And the simple thing here, we're just going to use tables because, as I said, one of them is experimental parameter, which we have it kind of ready. And the other one can come either from a chart or a table or a simplified formula. So as I said at the start, the steps and calculations we're doing here are really straightforward, but you need to know the meaning of what these means and how they're used. And then later on, as I said, in week 6 and 7, we will end up using this parameter. And we're going to go through these calculations again to use them for calculating one of the main things we're teaching you here is serviceability or deflections. Now, I've gone through these points, but just gonna retouch them again. The rate of shrinkage that will happen in a reinforced concrete section can come from different factors. The mix of concrete, as I said, some of those factors it's not within the designer's hands. Designers, they just need to make sure, especially for shrinkage, really, there is one parameter you need to make sure you're using, which is this one, which I will talk about next. So there's a parameter 800 over 1 million. It's just a strain value. It's actually a strain value, which is well defined in the standards. And if you're going to use this, the people who are going to supply the concrete, they're going to make sure that their material will end up following such parameter. And that's really, as a designer, that's what you need to adopt and make sure, considering when you do the calculations or when you're going to be picking numbers from the standard. So as we said, it depends on the mix of concrete to achieve the shrinkage strain parameter, the 800 figure that I was telling you, right? And the environment. Now, as we're going to take you through deflection and crack control over the weeks, you just need to have an understanding about what type of or what environments you're going to be the concrete elements going to be placed in. If you're going to have concrete slab within an internal environment, so it's not a wall or a car park, then that means it's internal. Then that means you have to go and design for moderate or internal environments. And basically, you will end up using a one line, like a very small relationship, to give you the correct crack control figures, full stop. That's all what you're going to be doing. Okay, so that comes to dealing with the environment. You're going to see when we teach you how to determine the number, the bars, quantities inside a slab, right? After you find it for strength, you have to go and make a crack control check. That crack control takes care of this point, right? So you're gonna make a small check, and that check will let you think about whether this piece of slab is placed externally, internally, etc. Whether it's for a swimming pool, for example, depends then on what crack control we need to achieve. Is it low? Is it moderate? Is it high? Then based on that, you're going to choose the correct formula and just double check that the steel quantity you had for strength is already doing this job for us. If you need more steel, then just increase the steel more. Okay, you don't add them to each other. So the crack control steel is not added to the strength steel. No, you just go to the worst case scenario. Okay, because the line of stresses are different. So that was point B. Point C here, it's just the size of the element, which that's what the formula I was talking to you about. It's in function of the width of the element and the depth of the element. You're going to see inside those formulas we're going to use at some stage later. It's in function of the width of the beam or the slab multiplied by the depth of the beam of the slab. So the size of the element will have, or typically has an impact on the shrinkage level. This is to do with the builder and how they're going to manage to cure the concrete on site. You need to understand if it was poorly cured, like not enough, if it was very very warm weather, like 40 degrees in summer. Usually builders and building practitioners know that when they pour in concrete, they have to make sure they either gonna carefully apply a curing and watering mechanisms or processes, or they will ask the supplier to add mixtures, some chemical materials, to make sure the water gonna stay even, gonna stay in the mix and slowly get evaporated. So the whole hardening process gonna gently take place, and you will have a proper shrinkage because if the water really get evaporated like in a short time without carefully processing the chemical reactions, then shrinkage will be very significant, and then you may end up the steel even you have for strength may not be adequate to control shrinkage, and that will cause the issue. Now you're going to see next when we talk about creep going to be in function of the load the beam or the slab is under. However, shrinkage is not. Shrinkage is only happening at the early stage of pouring the concrete. So it has nothing to do with load. And here we did not talk about loading. We just talked about the mix of concrete. We talked about the environment of where the piece of concrete gonna be. We're talking about the size of the element and how it's cured. But it has nothing to do with loading, unlike creep, and we will talk about creep next. So this statement here is talking about the main shrinkage strain we have to follow and adopt in our calculations. So, and this is experimental value, right? And it's well standardized. So it's typically used if you know, I don't want to open the standard now, but I'm sure you're going to see it over the worked examples. This figure is standardized by the AS3600, and the standard also said you either use this or change it based on an experiment. So if you're going to decide to change it for whatever reasons, it means that you have to clearly advise your suppliers that this is the difference, because in some states, you know, this figure depends on the aggregates available in the area, the type of water quality available in the area. Sometimes if you want to do concrete mixes in remote areas, and then the engineers there will understand that this is not achievable, then they have to use maybe 700 or 650. They need to define this on their drawings or on their specifications. So things will be matching what's really going to be used and what's designed for. So back to this figure, what does it mean? As I said, it means the shrinkage strain that the designers will follow. And if this was the case, it means for 20-meter long slab or wall, there will be this much of shortening. That's what the physical meaning or the practical meaning for this shrinkage strain. So remember I was talking to you about if you have a footpath if you have a footpath and say that footpath is about 20 meters long, then over the entire 20 meters, this slab will actually shrunk for about 16 millimeters, and it comes simply from multiplying the length by the strain. And last week we said to you the strain is a displacement over displacement, because the definition for strain was the original length. So it was the change in length over the original length. We had this from mechanics of solids. Okay, so if you multiply this by that's the definition for strain. If you multiply it by the original length, it will end up giving you the change in length, which is the 16 millimeters. And I would say if there are no saw cuts in this footpath, then cracks can happen because the slab want to open somewhere. The slab want to open somewhere because it's under tension, you're tensioning it. Then the solution, as I said, if it was on the ground, then you can use saw cuts with some steel. If it was only suspended, then you can only rely on the steel to resist such cracks. Okay, that's if it's suspended. Now, and I think you're gonna know from industry, the typical length of concrete people pour as suspended, it goes up to 30 meters. Then after this, they have to introduce some movement joints. Okay, so they will have two separate slabs. Okay, and while we're there, so if you have a slab and this is the column, you have to stop it and you can create a corbel. What does corbel means? A movement joint, like it's just going to stop like that with a step, and then your next slab will come on top like this. So this is why I'm calling it a movement joint. This is suspended slab because we cannot just do a saw cut from the top, right? We have to do a movement joint. And you would see, you know, if you walk in a shopping center or in a car park, you would see usually they put some plate on the top. You don't see it. You don't see that because they need to cover it from water, or they have to keep the slab, you know, allow it to move. So it's not, remember, this movement joint is not only for shrinkage. I'm talking about shrinkage here because that's the topic. It's also used for temperature and other measures, because even we need to allow for some movement due to impact, or if it's a bridge or whatever. So in summary, for suspended slabs, we have to allow for kind of a movement joint. Ideally, we go to 30 meters if it's reinforced concrete, and this is achieved by such detail. All right, that's just for your information, just to link the information we're talking about with what we have there. So the last statement we have on this slide is talking to you about how it's really calculated, or how your calculations will be done for shrinkage. It will be simply by calculating two types of shrinkage. One of them is the chemical shrinkage, and this is to do with the material engineers who follows the correct mixes and end up with the correct standardized figures. And usually this figure here, eta CSA, is autogeneous, or a chemical shrinkage. It's simply gonna be determined from tables, and you need to plus this figure with the drying shrinkage, which comes from another table or a formula from the standard. You add them together, that would give you the actual shrinkage the concrete would experience, and then you need to work with the shrinkage to check your steel reinforcement, etc., etc. Okay, this chart here just also reflect how shrinkage will increase over time, typically from the day you pour the concrete to the day you end curing. As I said, if it was correctly done, then the slab will not shrink, because you want the slab to complete correctly its chemical reactions. You want it to change from the liquid state to the hard state with correctly conducting all the, you know, with conducting the correct or leveled chemical reactions internally. I'm talking about internally, and you need to make sure it's got the correct water quantity to get this mechanism happening. Then from the day curing is ended, which is about 1 week or 2 weeks, then that's from where shrinkage gonna actually start, because there's still gonna be some sort of moisture, extra moisture inside the concrete, and that's where shrinkage will happen. However, if you have the correct quantities of crack control, things will stay intact, and those obvious cracks will be typically prevented. All right, if we're talking about slab on the ground, you can also introduce saw cuts, where you cut the slab at the upper part only of the section, or where you've got suspended slab, you will introduce movement joints. Now, another topic, the other behavior we have about creep, about the reinforced concrete sections, it's a creep. A creep, it is, again, it's about shortening the slab as well, or the piece of concrete. But the reason for it is different, right? Now, inside the concrete section, even when it's hard, I mean, we're not talking here about the day we pour it. So we're talking here about even after it's get to its hard state, they're gonna be micro voids. They're gonna be always voids, like a little air gaps inside a concrete, right? Now, as we mentioned to you last week, and as you know from mechanics of solid, if this was a piece of slab which is simply supported like this, it's going to be under bending. So we have a compression zone and we have a tension zone. Now, as you know, the top section, it's under compression, and the bottom section here is under tension. So let me show it. Sorry, it's just the same. I have to change directions here. So the upper side, if it was a positive bending like the one I'm showing you, the upper fibers within this zone gonna be under compression, and the lower fibers or elements gonna be under tension. So the creep starts from here. The concrete, which is the concrete section, which is under compression, will tend to get shortened. Why? Because we're closing the voids inside the within the compressed zone. So that's really the start of creep. Okay, and you're also gonna hear about creep in timber elements, because it's got naturally those voids, and over time creep is there. And the standards for timber looks after those problems. They will tell you if you're using F17, you have to allow for this much of creep strain. Remember, the engineering parameters we're using here is strain. So after I've given you introduction about shrinkage, I ended up telling you we want to calculate the shrinkage strain. Tick. Same thing with creep. The engineering parameter we after is the creep strain. What does creep strain mean? Strain means it's shortened. We're pulling the slab this way due to we are compressing it on this upper side, when we are compressing it, we're closing the gaps, those micro gaps. But they means we're closing it by fraction of a millimeter. But that fraction of a millimeter, if it causes stresses more than the tension the concrete can take, then cracks will happen. To avoid those cracks, same thing, we can control it by steel, etc., etc. And that's basically the reason behind the creep and why it's happening in concrete. In simple words, there are voids inside the concrete, micro voids, and they will get closed due to sustained load, due to a compression. I know slab or a beam is under bending, but the upper side, if we're talking about positive, the upper section above the neutral axis, it will be under compression, and that will actually cause the creep strain. Okay, so we're closing those micro cracks or voids. So that was basically the idea behind. Now, as we said, like shrinkage, creep, if creep is restrained, And we said to you, what does restraining means? Because maybe the slab is supported on a wall or a column or another steel like a beam or also concrete beam. Then you're restraining it. You're preventing it from freely getting shortened, okay, and changing its length. So because of this fact, you will cause cracks and things, and whatever I talked to you about shrinkage will happen for a creep as well. And eventually, also like shrinkage, creep will cause deflection. And that's why, again, in week 7 or 6, when we're going to talk to you about deflections, we will touch on these two strains components, the creep strain and the shrinkage strain. They will be called when we do the deflection check. We will not talk about shrinkage during the design process, only at the end when we check the crack control, as I said to you, for shrinkage especially. For shrinkage, we're gonna make a check for the crack control at the end. However, for deflection, we will again recall these parameters to see how many more millimeters the slab or the beam gonna deflect due to whether creep strain or due to the shrinkage strain I covered before. The rate of creep strain or the occurrence of a creep will also rely or be related to some factors, and the main difference between creep and shrinkage is creep is in function of the load. Obviously, as I said to you, we're closing gaps here. Yeah, we're closing gaps due to the compressed area. Now that closing gaps in the compressed area, it's coming from where? It's coming from loads, right? It's coming from applied sustained load. So, and that was different than shrinkage. Shrinkage really has nothing to do with load. It's just about the early stage of the concrete where it's drying. That's where shrinkage is taking place. Creep as well. The age of concrete, it's always going to creep a lot during its early stage because you know, at the early stage, that's where the concrete will take its more load. You will see, and maybe we talked about this last week, usually the dead load is more significant than live loads. Why? Because part of the dead load is the own weight of the slab. Especially in the early days of the concrete, if you have a piece of concrete, when you're going to build it, you're going to build it sitting on top of the props and the scaffoldings. So it's sitting on special tables, and then you're going to pour the concrete and you're going to leave it there for 1 month, 28 days. Then you're going to strip and take away the formwork. Now, this is the early stage. At this stage, the heaviest load or the most of the load, sustained load. When we say sustained, that means it's going to stay there always. Live load, you just have people walking and then going away. Live load is moving load. But sustained load is a staying load. And by the time you strip at the day 30, that's talking about the early stages or the early age of concrete. When you're going to strip it away, it will get impacted by the first load a concrete slab or beam or element can experience, which is the dead load. Usually it's heavy load, and that's where the slab will experience a bit high creep strain, eventually high deflection. So usually slabs will deflect, and you're going to see in our design when we get to deflection, there is a simplified steps where we can allow for a creep. Sometimes it go by multiplying whatever deflection is calculated by 2 due to creep. So this just to let you feel how the process of applying the dead load onto the beam will cause significant deflection due to the creep strain. Same thing also, creep is also related to the ingredients inside the mix, but again, that's looked after by the supplier. So The two parameters, which on the next slide here, this is from the standard. As we said, this is the creep strain. And again, this strain will help us to determine the level of shortening the slab will end up being experienced and eventually deflection. So step by step, this creep strain, right, will give us a figure about the overall shortening the slab is under, or column or beam, and then that shortening can be re-simulating the sagging or deflection. That's how it's working. Now, this parameter is a function of what's known to be the creep strain over the initial elastic strain. These two parameters, they are well defined in the standards. And we will go through these tables or formulas that will take you through the exercise. Now, I was talking about this curve in my, previously I was saying to you, usually when you're going to apply stresses, applying the first stresses a beam going to take is by the time where you're going to strip and take away the scaffold from under the slab or the propping components. And that's where you're going to see you have this sudden change in the or sudden increase in the creep strain, and then over time it will get smoothened as you go with time. It's unlike shrinkage, where shrinkage was kind of got a different curve here. It's kind of non-linearly increasing over time, but eventually they will end up all flattening at some stage. We're only worried about the early stage where the design need to be correctly made. So we've gone through, as you can see, not too many mathematical expressions or relationships, and you're going to experience the use of these relationships in the examples. This section, again, a small section before our examples, it is to do with durability. And it was the third item we want to cover here. After this, we have the cover. The durability, simply you don't do it only for reinforced concrete section. You want to have a durable, anything you want to buy, you're going to think about its long standing and the durability, whether a vehicle or a watch or a phone, whatever. The same thing with reinforced concrete. The engineers need to understand what's the business and what's the service for the concrete element they are designing, whether a slab or a wall, or is it for a house, is it for a shopping center, is it for a swimming pool? And then they have to go to the standards and determine what durability class they need to follow. If you know the durability class, you will be like in the last slide here, we're saying the standard has classified durability for us from 1 to U, 7 classes. This one is the lowest durability, and it maybe this one will be typically for concrete slabs, for internal environments, and sometimes those slabs are covered with carpet. So it's really going to be looked after in terms of its impact with environment. So we will come to this. So basically, the durability can also be defined as the resistance to deterioration or the life-standing capacity for that element. And how to control or achieve acceptable durability. You can see here 3 definitions: high quality design, high quality materials, high quality construction. As a designer, obviously, high quality design. To make it simple and straightforward, mostly the engineers to come up with a quality design is they're going to specify the correct strength. They're going to specify the correct cover of the concrete, of the bars, of the steel bars, the cover, which I think I mentioned to you earlier. So these are the 2 main properties. There are other things, and also there are someone going to tell me, do we need not to talk about the curing process and all these kind of things? You're going to have a standard document which is done for many jobs, and you're just going to reuse it. It's just like a Word document or a report, a specification, which you're always going to remind the builder and the suppliers that that I have designed this slab for this class, and as per the standards, this class needs to have this arrangements for curing, this arrangements for admixtures. So there are other things, but it's just about more to do with the mixes. And typically what I was trying to say, the contractors and the suppliers will worry about the second and third factors. Okay, they are all important. You just need to, you don't need to design nothing for them. You just need to refer to them somehow on your documents. But most likely in terms of calculations, we worry about cover and the strength of concrete. Okay, as we said here, it is mostly durability to do with environment, and those 7 classes I covered, like I showed you just before. 7 classes depends on whether it's internal, whether it's external, whether it's exposed to running water, right? Whether it's exposed to soil with chemicals or without chemicals, they change. The worst case that you would see is a concrete impacted by acids. And the slides will say this clearly. This is considered as class U. And if you go to the tables, class U, which is the last worst case scenario class, it's not covered by the standard. It will ask you go hire chemical engineers to solve this problem. Like I tell you, you're just going to end up painting the concrete with some special products to let it resist such attacks. Okay. Surface attack, surface defects. What this statement is telling us here is, which is also a builder responsibility, is sometimes damages can happen to concrete and they need to be fixed, whether during construction or after construction. You cannot keep it without. This is, again, it's not really an issue as a designer from day one. Chemical attacks, I just talked to you about this. Ideally, or structures or slabs or what we're going to practice, they won't have such attacks. But if there are attacks, then you may end up having this classified as class U. Class U means it needs a special treatment. You can not only control it by good cover and concrete strength, even if you used 100 MPa, you have to manage to do other provision like paints or other covering requirements. This statement here is talking about, again, impacts or damage, which it's similar to this point here, which it needs to be treated as required. The last point we're referring here, and the standard actually referred to these things, is cycles of freezing and thawing. This is usually in cold areas where as I said, inside the concrete, we have voids, the micro voids, and at some stage, these voids can be filled with water. Now, if it's a cold environment, the ice will expand, and that ice will cause, expansion for the concrete, and cracks and spalling. Spalling means some sort of cracks that will, I think I've had a quick image, just opened it. If this is kind of what they mean with spalling, it's just some reflection. You see them in very old or aging concrete because the durability have been compromised for whatever reasons, aging reasons, or misuse or impact that was not treated. So at that thawing and freezing point, again, it can happen, but it's not likely to happen within the area, like in maybe in some areas in Victoria, where there is a snow and all that. But how to you just need to follow the standards and use the correct mixes and the correct arrangements we can have from there. This slide got a very simple but really good message that I would like to share with you. If we focus on this graph, there is some sort of chemical process where it will take place over the age of the concrete, which is the carbonation. So carbonation will happen whether you like it or not in any piece of concrete, but what they're saying, and that's how it can be related to making the correct decision on the cover. So if you, for example, miss the cover by 2 millimeters only, right? If you miss, if the standard, if you follow correctly the standard and standard says adopt 25 mil cover, however, the builder, not you, the builder ended up not doing a quality work and ended up having 32. Sorry, 23 millimeters. So we're just missing. So I was saying ideally you needed 25, but he ended up using 23 millimeters. So he missed 2 millimeters. That means the age of the structure is compromised or reduced by about 10 years. So 2 millimeters would cost 10 years reduction in expected life. Now this is published by textbooks and it's well known in the industry. However, I would say there are builders, if they building prestigious structures, they're always going to bring qualities and add mixtures that can change this relationship always. So in decent or higher or prestigious structures, they're always going to spare some monies to deliver and have add mixtures, chemicals added where such carbonations won't have that impact. So just to let you know, these kind of things may be possible 20, 30 years ago, but nowadays people really, got those chemicals to carefully look after such issues. Now, just more to touch on, quick things to touch on durability. We're talking here about chemical different reactions. Like I think I've already covered some of them, like the relationship between acids and concrete. There are also other chemical reactions that can end up causing such outcomes, which is eventually the spalling of concrete and straining. It's just the aging, and that's where even as a designer engineer, you're only going to provide insurance for 10 or like 7 years, but usually the owners need to maintain their structures, or whoever the stakeholders, whoever looks after a building. So any crack due to shrinkage or due to impact, whatever, they should be treated accordingly, and things will stay durable for the expected years. All right, because there are, if there was a crack which never treated, it will eventually end up allowing for more chemical reactions to happen. For example, this alkali silica reactions, if there were gaps in your finishes, that will allow for some reactions to happen. I think we've got one quick slide, but I can say we covered most of, and we will go through this table. This is just a quick view for one of the tables you will experience and find the answers we want. In summary, as a designer, or what you're going to be asked in test 1 or 2, the two and the final exam, we will ask you in one of those exams to design for a durability and shrinkage and also fire, which we're going to talk about in the second half of today's lecture. Mainly what you're going to be doing is finding the correct cover and ensuring your adoption for the correct strength, the MPa that we talked about last week, and also using the cover. So after this is one of the tables, there's another table which will show you how to use the correct cover, and basically it will cover most of these definitions for you, because eventually it will end up determining the quality you are expected to follow. So I think that was my introduction, people.
I think it's not working. So let's say, I hope you can see my screen. Let me read this example first. These examples are given in the lecture notes. Determining the concrete compressive strength, FC dash. So we need to find the concrete compressive strength, FC dash. And cover options for evaluating the durability. So we need to specify two things: FC dash, concrete compressive strengths, and we need to say what would be the cover, minimum cover that is required. So it is an office buildings given, because your architectures and your surveyor will mentions about whether these buildings will be office building, residential buildings, and so on. And where it would be located, that also you can find from your architecture surveyor. It's in St. Kilda, Melbourne, which is approximately 1 kilometer to the coast. It's very coast, where the building will be located very close to the coastline. Part of the external columns, external face of the external concrete shear walls are exposed to the environment, but remaining structure is internal except for a brief period during the construction. So what does it say is that your outside perimeter of the office buildings, that's include the shear wall, concrete shear wall, that's include the outside perimeter beams, columns are constantly exposed to the environment, outside environment. That is external perimeter. Internal, if you have an internal slab, internal beam, internal columns, they will not be exposed to the outside environments after the construction. During the construction for short period of time, they will, but after the constructions, it's a closed buildings. So they will not have a significantly exposed to those outside environment. Now we need to consider columns, beams, and slabs from the first floor and above. So we're not talking about the ground floors. As Heather mentions, there are slabs sitting on the ground floor, like contacting with the soils and so on. So it's not part of these examples. Do not consider the ground floor, foundation, and footing. So we just need to talk about what concrete compressive strengths we need to specify columns, what cover that we need to specify for columns, what concrete compressive strength for beam and for slab, and what are the covers that satisfy the requirement of durability. Durability means the structures would have the life of the structures that we like to provide through these covers, right? So to start with, let me share some thoughts. All right, I hope you can see my screen. It's a little bit small, so therefore I told the students to open the standards AS3600. Tomorrow in the workshop, please bring the printed copy of AS3600. It's allow you to work with me and with in the face-to-face or whatever. We like to experience these standards while you are sitting in the lecture and the workshop. So open your standards and just open the section number 4 for us, because the section number 4 is dedicated for the design for durability. So these weeks we're going to look at the section number 4. In the standards they call it section, not chapters. In these they call it clause 4.1, 4.2. Now, one interesting fact that durability has become the major concern in last 2 to 3 decades. Why? Because last 20-30 years we are more talking about the durability. There is not so much important in early days. In early days, in old structures, you have seen, even if you are in Bendigo, there are many old buildings, right? So they are designed based on working stress matters, meaning that they are bulky. You can see their size of that columns or beams or slabs are huge, and they are based on working stress matter. Working stress matter meaning that they don't consider this plasticity and all sort of things. So they are big structures, and steels are used for mild steels. They are soft, 250 megapascal mild steels. So if you use mild steel under the service load, you will have low strengths, right? If you draw the stress strain curves, you will your structures. If you see those old structures very bulky, they have very small strain. They don't deflect. It's very rigid. So if you have low strain and then you have less deflections and less curvature and less cracking, so you will have no cracking. So those days the size of the columns are so big that they don't make these durability checks. So that's the importance of durability. So before we don't have these chapters in our start of the Australian standards. Now in last 20-30 years we are adding these durability chapters significantly. Now for requirement of these sections apply plain reinforced and pre-stretched concrete, member will design for 50 years plus or minus 20%. So generally speaking, if you follow these procedures, the design life of the reinforced concrete structures would be 50 years, clearly specify here. Now, method of designing for durability. There are steps given to you that you can clearly follow true, right? So you don't need to remember when you are designing for durability. First step is to find abrasive from the traffic. That's the first steps. You check whether your slab, beams, column, your structures, the concrete will have this abrasive from traffic from clause 4.6. So if I go to the clause 4.6 for your completeness, abrasive, you can talk about footpath, commercial industrial floor, pneumatic tire like a like a forklift or this kind of activities, steel traffics and so on, this kind of activity. But in our examples, we are not designing such elements for the concrete, so we just say that abrasion is not. Let me turn off my camera, please. So I will I will turn it off and I will just flip this one. Now it says that first steps we need to do it is abrasion. We need to check abrasion, and for our case it is not applicable. We no need to specify anything for that. Second, I will show it to you here. Now step, we go back here, how to do it. Now first steps we done it. Traffics and all, we don't need to worry about this one. It's not applicable in our case. Members of the cycle of freezing and thawing shall satisfy the requirement of clause 4.7. By the way, let's put the clause 4.6. Clause 4.6. Next one we will have clause 4.7, and I will share with you the freezing and thawing. Now there is a we not too much worry about this as well. As you can see, there's a special cases like it's if your concrete will experience this kind of a freezing and thawing cycle. Cycle of freezing and thawing, concrete need to be comply with this one. So we not worry about that one. It's not specifically if your architecture or surveyor just specifically mentions that they will be exposed to any freezing and thawing. It's like a cold environment. It's like sometimes your night temperature minus 20 degrees Celsius, in the daytime it goes to the 10 degrees Celsius or 20 degrees Celsius. So these cycles will cause the brittleness in the structures. We generally conduct a test here in the laboratory for freezing and thawing. What we do, we take an aggregate and we put it in the refrigerator for 16 hours, minus 20 degrees Celsius, and then we put those aggregates for next 8 hours into the outside sun or environment. So that's you can see how the concrete is losing the materials. That's how we calculate those freezing and thawing the resistance. But in our case, it's not applicable. And that is taken from clause 4.7. Now next is we're going to talk about these aggressive soils and also I will not going to write it, but I just going to read it for you. That it just need to talk about aggressive soils. As I mentioned, we are not talking about the ground one. Alkyl aggregated reactions, and also it's depending on the soils that is coming into the context, so we don't need to worry about that that sort of things. Now let's go back here. Durability shall be allowed, design exposure classification negotiation with the clause 4.3. So now let's talk about this exposure classification 4.3. Now there are I hope you can see my screen. There are 7 exposure classifications that is Australian standard specify in table 4.3 exposure classification. What are they? I'm going to explain you. What are those 7? Start with A1, A2, B1, B2, C1, C2, and U. By the way, you don't need to remember those, how many exposure classification, what are those and all. They are all given in the Australian standards. In the test, in the final exams, you are carrying these Australian standards. Please don't write anything on the Australian standards. You can highlight something. This writing is just for me to explain in case if I miss any detail. So these are the how many C1 exposure classification. They are in ascending order for severity. What does it ascending mean? So when you see A1, they are less severe. Less severe meaning those structures. If your structure sitting in the A1 zone is less severe, it's not aggressive. It's not aggressive means it is not damaging your concrete. It's not corrosive environment. As you go further, like A2 is more severe than A1. If you go more further, it will more severe than A1 and A2. So what I suggest that these, when the severity increase, the concrete compressive strength and cover will increase. The amount of cover goes, the requirements will increase. That's what it's specified. Of course, this U is the extreme, is the severe one. Now, if you want to see how they are dividing it, there are surface and exposure environment. There are 1, 2, 3, 4, and total 5 and 6 different surfaces. The first surface is that contained in the ground. On the ground levels, what are the surfaces? And this classification does not require for our examples. The surface of the member in interior environments. So, of course, if you have a, let's say, beam or columns or slab sitting inside, like if you come onto these ET buildings, Bendigo students, we have this ET215 room, we are working on the slab. So that is internal environments. I hope you understand the internal environments. For residential and non-residential, you have A1 and A2 classification. And for industrial buildings, there is a B1 exposure classification. So it's easy to read, just to read and making judgments. If you are confused between these two, like if you are sitting very close to each other and say, I don't know whether I choose A1 or A2. So if you are not making decision between these two, I would go for more severe case like A2. Choose A2 because it's conservative. So in case, because it's not, this is just the guideline, right? In some of the cases, your case might not fall in some of this category. So you find closely matched, and within that closely matched, you can find a severe one. Now the third one is surface on the member above the ground. So let's say on ET buildings or in your buildings, you have level 1, level 2, level 3, that is above ground. Inland, which is 50 kilometers from coastline environment. For example, Bendigo, it's inland greater than 50. You have different non-industrial with arid, temperate, and tropicals. Now I need to explain those three different climate zone. So if you turn the page over, and you have figure 4.3. In these figures, the map of Australia is given. Here, the map of Australia is given to you. The whole map is divided into 3 zones. Right? So that 3 zones are given from the Bureau of Meteorology. Now you have, if you are in this zone, temperate meaning that moderated rainfalls. You don't have heavy rainfalls in this temperate zone. Arid is having little or no rain. So in this zone, you don't have much rain, like Alice Spring and so that deserts. We don't have Western Australia or some part. We don't have too much rain in this zone. So that is arid. North side, like Darwin and Queensland, they are heavy rainfall. So they falls in tropical weathers like a crosshatch. So you have tropical weather. So based on the, look at this. This is less severe. This is more severe, most severe. You can see these classifications as well. Because if your concrete is exposing more rain, it has less life, because concrete don't like waters. If there is a crack, water goes into the reinforcement start cracking, the bond between the reinforcement and concretes are gone, and so on. So and that's how it start causing the trouble. So if you are designing something here, same buildings, if you are designing here, you need to provide more concrete compressive strength and cover here if you have same load. So I hope it is makes sense. So here you have classification for those near coastline, 1 kilometers, B1, and so on. So it's a self-readable. I hope I give you the enough guideline that will help you to help you to expose. So let's do this exposure classification, and for these exposure classifications we are going to use table 4.3 of AS 3600, and for this case we have external exposure classification and we will get internal exposure classification. Let's read from the table that our buildings is in Senkilla, which is 1 kilometer to the coastline. So let's do the external first. So let's say interior environment, non-residential building A2. For interior environments we have A2. So let's say interior environment A2. Interior environment A2. For exterior environment, so I'm just take it here, interior environment, office building, non-residential building A2. For exterior environment, near the coastline 1 kilometer to this one, any climate zones, so don't worry about the climate zones, then we take it I think we just need to go for coastline, see note number 5, because this is near coastline and this is on the coastal line because it's 1 kilometer. So let's take it B2. As I mentioned, we are confused between whether we should go for 1 kilometers or we just go for coastline. Yeah, so there is a critical decision need to be made here, because whether we go for B1, B2, because B1 said 1 kilometer, so we are on 1 kilometers. So if someone just measure it, how they measure it, so I would go for B2. I think note number 5. For the purpose of the table, the coast zone include within the 1 kilometer of solar exposure of salt waters and so on. So as I mentioned, so I think how you read it, but I think for severity we go for B2. So therefore let's choose a B2. Right now, so all are good now. So let's start working through the next one. So I hope you understand how to extract the exposure classifications. Now minimum strength, let's go to the table number 4, minimum strength and curing requirement for concrete. Now let's use this table 4.4. Number 4, we want to use floor surface, let's say. Now because that is internal, inside is internal, so classification is A2. We already find it out, this one. So for this classification A2, we can find here from table number 4.4, minimum strength and curing requirement for concrete. We have exposure classifications for internal surface is A2. For that, minimum is 25, curing continuously for at least 3 days. We are not asking the question, not asking about curing, but you can read through. And minimum average compressor at a time of seeping from the formal to the mold. So I think we can specify minimum FC days to 25 megapascals. So that's table 4.4. It says that you need to specify minimum FCDS equal to 25 megapascals. Now, how much cover we need to provide for internal surface wall? We can go to the table 4.10.3.2. I will show it to you here. If you go back here, tables required cover when standard formwork and compactions are used, or there is a required cover where effective procedure and intensive compaction or self-compacting concrete are used in the rigid formwork. So between these two, you can make assumptions. I'm just making assumptions that we are using standard formwork and standard compactions are used. So for that case, we have A2 classification internal, and we have selected 25 megapascals minimum concrete compressive strength from the previous table. For this case, we need to provide minimum cover of 30 millimeters, as you can see in this table 4.10.3.2. So oops, sorry. So table 4.10.3.2, we will get cover 30 millimeters for internal environment. Now let's do the beam, because it's asking me to find the values for beams. Now for internal classification is A2, and as I mentioned, we will get the concrete compressive strength FCDS 25 megapascals for beam, and we're going to provide the cover 30 millimeters. So these are the internal beams. For external beams, what was the classification for external beams? Let me check. Classification for external beam is B2. So classification for external beam is B2. For B2 classifications, if you go back here and you want to specify the concrete compressive strength 40 megapascals for B2, 40 megapascals, and by the way, this is external beam, and the cover that we need to get it for B2 cover for B2 40 megapascals, we need to specify 45 millimeters. So I hope it is clear for you. Now let's do the columns. Again, internal columns. Classification is A2 for internal. For that case, we have FCDS, just repeating, 25 megapascals minimum, and we're going to provide cover 30 millimeters for the columns. Internal, external, we will have B2 classification. FCDS for B2 classification is 40 megapascals. We already specified that in the beam. So same thing, cover is 45 millimeters for the columns. Now for columns, I want to just clarify a little bit more, because sometimes when you have a connections between the external columns and walls, we sometimes need to provide some extra covers. So these need the extra cover to provide connections with column. So for that case, for external only, that's we need to provide the connections. We put 45 millimeters and we put extra 15 millimeters to accommodate that. So we go for 60 millimeters covers for external columns. Now for walls, I think we done. I think the question is asking beams, columns, and walls. Now walls, for internal walls, again I'm repeating myself, but just for the completeness of these examples, I'm just writing it all up. A2 classification for internal. For that case, concrete compressive strength is 25 megapascals, minimum, by the way. This is minimum. For strand purpose, we might need to increase this one, but for any reasons, any smart engineer say that I want to use 20 megapascals, not allowed. That's what I meant. You need to start with 25 megapascals to satisfy the Australian standard for durability. Of course, you can use 32 megapascals and 40 megapascals and so on for your strand purpose. If it is, we will do the strand checks later in this course, but we need to start with 25 megapascals. That's the minimum requirement. And again, cover, minimum cover, by the way, is equal to 30 millimeters. I know you know where these numbers are coming from. I already show it to you. And external walls, again, B2 classification, minimum FC- is equal to 40 megapascals, and for cover, we just allow these connections to be happen, and that's therefore we have 60 millimeters minimum cover. I hope it is makes sense now. Let me know if you have any issue there. Let me turn on before we start with the fire resistance topic. Look, the durability is very simple but very important. So we can't very simple in the meaning that it does not have any equations. It does not require any. It's just reading the tables from the Australian standard, and there are not many tables there. It is self-explanatory, no equations. The things that I need to explain, I already explained to you. I think I will share with the screen with you. So this section number 4. We talk about this first page number. You explain between the line. You read between the lines. They are easy to read. Again, you can read through this one. I already mentioned briefly. I think you understand this map as well. Some requirements: abrasions, freezing, and thawing. So we use this one to calculate the minimum strength. These tables are used to calculate the minimum strength. We have not touched based on this. We use these tables to calculate the minimum cover. And I think that's pretty much straightforward sections for you. Very important. And this is the starting point generally in any project. This is a starting point that you need to know what is the minimum that you can't go below, right? This is the starting point. 25 megapascal strength, no argument. You need to use those minimum concrete compressive strength regardless of your strength requirements. So you can't go under. All right, now that's all good so far. Let me share the screen with you for fire. Both incident external column and wall have to be 50 millimeters rebate at the construction joint externally as shown in figures. So increase the external capacity to allow for rebate of construction joint. So generally some only require just a 45. I just give you additional information. So this 45 and the 15 millimeters is not what can I say? It's not our any. It's just the engineering judgments that you make it depending. But this is not our. What can I say? In the exam or in the test, you don't need to come across that you need to make an assumption about the joints and all. The 45 millimeters that you specify will cover 60 millimeters. Right? So if you say that your minimum cover is 45 millimeters and then later on during the construction or during the designs you specify 60 millimeters, you still make the Australian standard happy by saying that you are providing 45 millimeter minimum cover.
Yeah. Okay.
So the cover would these concrete compressive strength and covers are not the final one, by the way. These are the minimum requirements that we are setting it up. So later on in the subjects, you will see how we are changing. This is the iterative process. You will see how we change those values for the strength requirements, because this durability is not a safety concerns. You know what I mean? The structures, these things that we specify here, It has nothing to do with this one. The structure might fail. So the critical situation comes when you want to make our structures safe. That time we need to make sure that strength and covers are adequate. Okay, does it make sense?
Yeah, that makes sense. Thanks, Vipul.
Okay. No problem. So this is just the extra. You can ignore this one for your for test or for exams. Now fire. Now for fires, we are dealing with three things: element strength, fire integrity, and insulations. You might say, does the standard gonna tell me? Because I can read your mind now that now everything needs to go to the standards. I agree with you that everything needs to be go to the standard. So section number 5 dedicated to the fire resistance. By the way, for your information, concrete has both low thermal conductivity and high heat capacity, which is good. Now it has yes, there you go. It has a these insulations, integrity, and structure adequacy, right? So those are some of the definitions that I'm going to mention for the fire resistance. That if you come on the clause 5.2.6, they talk about this, which I'm going to mention in here. So under the fire conditions, your concrete should be strong enough. It should not fail. And your surveyor going to tell you that how much strength do you need for resisting these fires. Does it 60 minutes, 30 minutes, 90 minutes, 120 minutes? Based on that, you will provide the concrete compressive strength. Does it make sense? So when the building goes under the fire, based on your design that you're going to initially design, that it will not going to fail for next 60 minutes. So the occupant or the users will going to exit the building safely. The fire truck might arrive on the sites before that, but for safety reasons, the surveyor will specify what period that the concrete would be strong enough to hold. That's the first thing. Fire integrity, loss when excessive large crack through the element. So then next questions comes that for the next one, because let's say you say that for 30 minutes you will be strong. For let's say 60 minutes, you will be strong for not creating any cracks, right? So the user don't see any cracks for 60 minutes if the fire goes on. And then you have insulation for let's say another 90 minutes, you provide the insulations for that not to happen. So when you are designing this fire, you have 3 components to look, and that is given on the standards. I already showed it to you. So that's strong enough for that particular period that you're going to design. It should be not crack for that particular period and should not be insulated. Again, how do we going to control this one? By providing the minimum concrete compressive strength and by providing the cover. There are the 2 main functions. There are the main 2 elements that we're going to cover. That what would be the minimum concrete compressive strength that I will provide for strength, for integrity, and for insulations that will resist. How much cover I would provide to accommodate those levels. So fire resistance period, this is defined in times, in minutes. So the surveyor will not going to write like this 30, 60, or they will not write minutes, but you automatically understand their unit is minutes. So limit state fully developed exam keyword 30 minutes, 60 minutes, 90 minutes, 120 and so on. So that is the fire resistance period. So I think they mentioned fire resistance period here. Now fire resistance period, time in minutes for a member to reach appropriate failure criteria. Structure adequacy, which is your strength. Basically, structure adequacy is how strong it is. Integrity, should not crack. It should provide the insulations enough if the test of accordance with the appropriate standards. This one, fire resistant, fire separating functions, insulations, and integrity and structure. Maintain structure function when exposed to the fire. So that's, you can read it, but this is the 3 things that you need to mention that one. Now fire resistance level, this is a fire resistant that structures adequate integrated this one. So generally they will specify like this: 90, 60, and 60. That's how they're going to specify in the in the surveyor that will specify those values. So first one, let's say this first one will going to go for strength, second one will go for integrity, and third one will go for insulations. That's that's how they specify, and they are in minutes. So I hope it makes sense. Again, fire resistance, three criteria that we look for. The units are in minutes, not will be written on your document, but it's automatically saying in the standard, so they are minute. And based on these ones, you need to specify the minimum concrete compressive strength and cover to control this fire resistance. All right, now given below, the requirement of primary structure for beam, slam, column, walls are given. These specify both minimum thickness and cover of the main longitudinal bar. Again, round up the suitable standard bar chap. Now, how we do the how do we do this cover? So it's called bar chair. Generally, we have this kind of a bar chair. So these kind of a bar chairs are available to maintain the cover. There is standard bar chairs. So you put this is the cover that you specify, and they use this bar chair and pour the concrete, so it will develop the cover. So you need to specify something that is available in the format of bar chair. If you specify, let's say 20.5 millimeter cover, and there is no bar chair available, then it would cause some construction issue. You need to have an idea of available bar chairs. So that's what mentions in my slide. Now let's quickly do these examples now. So determining the concrete compressive strength, again same thing, cover options for evaluating fire resistance, same example, same building, same location, office building, but before example was durability. Now let's do the fire resistance. In sand killers, 1 kilometers external, these details we already discussed, so not reading it again. We just need to again do the columns, beam, and slab, first floor and above. Office buildings, 20 minutes of fire ratings. You can see that for 120 minutes should be strand, should be insulated, and should be integrated. It should have integrity, not crack, strong enough, and should be insulated for 420 minutes. Beam width is 420 millimeters. Assume R10 fitments and reinforcements, column reinforcement, and all the details are given here. So now it's again reading the tables, no equations, no logics, nothing else, but it's just very important for you to check. Now, before we go I just want to explain the axis distance. Now the standards will gonna give you the axis distance, this average axis distance, average for depending on, because this is the fitments, by the way. This is the fitments. Probably when you do the workshop and the test, we will show you, I think, in the real world, the fitments. And these are the main reinforcement, longitudinal reinforcement, and these are the concretes. And this is cover. The standards will going to specify this axis distance from the center of the Rio to the out surface of the concrete. So this, and then we can calculate the cover from this these fitments. Now, let me take you through the first beam. Let's say we have beams first. Now for beams, we can go to table 5.4.1.b here, and I can show it to you. Fire resistance period, FRP, for the structural adequacy for construction of beam. FRP given in our examples, 120 minutes. There are various combinations are given to have a AM and B. AM and B Now for our case, we have 450. So for that case, our access distance is 35 millimeters, because in our examples it's given beam is 450 millimeter wide, and for that 450 millimeter wide, 420 millimeters of 120 millimeters of period, we will have a access distance of 35 millimeters. So you can see access distance AM is 35 millimeters. Now, once you know the access distance, AM access distance is 35 millimeters, we can calculate the cover, because your builders will not know access distance, they need the cover. So for that case, let me draw a little picture here for beam. We have fitments for beams, and let's say this is the top rio and this is bottom rio. Now we have AM access distance here to here, which is 35 millimeters, but we are interested in finding this cover C. Now to find this cover C, we can have 35 millimeter, take away this half diameter for this 20 millimeter rio. So 20 divided by 2, that's because this is 20 millimeters, by the way, and take away this fitments is 10 millimeters. R10 is a 10 millimeters, so 10 millimeters, we get this C. 35 take away 10, you get 25, 15 millimeters cover, right? But if you look at our previous one, that for beams we need to specify at least cover internal one 30 millimeters. So for that case, and external 45 millimeters. For that case, for fire you need 15. So for beams, we might say that we can take maximum of, but if you are just asking for fire, you just need 15. But for completeness, 30 millimeter, 15 millimeters, we can specify 30 millimeters for beams. But for fire, if someone specifically asks, that is the minimum cover that you need to protect your beam getting for 120 minute fire resistance level. Now for columns, we can use the table number 5.6.3. Yep, here you go. Table 5.6.3, combination of column exposed to more than one side. So let's say you have more than one side and you read UG equal to 0.5. In that case, our size is given 120, so we will have 120 here, and we will specify the size of the columns given to us in our examples. Now the size of the columns is 450, so you come back here, 450. So we have 450, and for that case, access distance would be 40 millimeters. That is given here, access distance. In that case, we can just calculate again the cover. Cover equal to 40. Take away the reinforcement is 24 and 12. So 24 divided by 2, take away 12, you will get 16 millimeters. Again, check with this standard bar chart and for durability. For slabs, we can go to table number 5.5.3, and this is by the columns. I think there is a case. I think we need to make an assumption saying that which kind of a slabs that we want to fire resistance for structurally solid and hollow core slabs, or we want to have a structure two-way simply supported rib slabs and so on. Based on, I think in our examples is given. Anything? Continuous, the slab is continuous and assume for n and 12. So probably continuous and one-way slabs. So let me check if there is a one-way slabs and all. So you have these one-way slabs here, and for that one-way slabs, I think the Surface Pro is getting warm up. So it's 5.5.2. If you go there, you will find that for continuous slabs, one-way and two-way is 20 millimeters. There. I think my Surface Pro is not working. So I think if you have a standards, if you go on table 5.5.2b, I think tomorrow in the workshop I will show you that one as well. You will find 420 minutes combine continuous slab one way and two way. You will find 20 millimeters of axis distance. And by the way, in the slab we don't have a fitments, so we just need to divide by Rio. So it's 14 millimeters. So that's the overall